Welcome to the IMTS Sparks Okuma's Eye Efficiency Seminar. My name is Errol Burrell. I'd like to introduce Ron Ranaszewski from Okuma, Chris Kozel from MasterCam, and Tom Rahn from Iscar. And today we're going to be discussing how all three of us have made a partnership to actually do this demo, and we're going to be showcasing exotic material, in this case titanium, and exactly the new methodology and how we can cut it and save you time and save you money. So let's talk about how the three components all come together, and we'll also talk about how this collaboration came together as well when we finish off this discussion. So I'd like to start with Ron, with one of the main components of this collaboration, which is the machine tool, Ron. And how's this machine tool? Why did we choose this machine tool for this particular demo?
The M560 is probably one of the biggest selling machines that Okuma has. And the big thing about it is it's like 18,000 pounds, and the way the structure's made, it's symmetrical for thermal growth issue, but the rigidity factors that are built into it, that has our Okuma built spindles, motors, and drives. So we picked it due to the fact it can do high speed and high power type cutting.
Yeah, and I don't want to get my salesman hat on, but one thing I want to say from the outset is that we sell it as a commodity machine, but it's a bridge built machine, isn't it? It's a very quality, it's a high quality made machine, which is accessible to many different types of customers. The small shop to the high-end shop. It's a very affordable machine.
Yeah, I mean, we sell probably more M560s and Geno's product in general than anything else per month.
Right. So now we've got that part of the actual equation, is the machine tool. So next thing I want to talk about is the programming, and that's what I'm going to point to Chris from MasterCam. So you did the programming for this titanium part. So can you just explain exactly what went into this?
Yeah, I mean, it was actually kind of an interesting project when we first started talking about this. It was, okay, well, what do we want to accomplish? And, what we're looking for is to achieve the highest material removal rate. So with that in mind, we kind of all sat down, talked a little bit about it. And, the subject came up of, hey, what's in your toolbox? What can we use to achieve, high efficiency machining, highest material removal rate? And oh, by the way, we're going to do this in titanium. So you've got to kind of understand the three elements or the three different techniques that we can use. And I want to point out, and Tom and I talked about this, this isn't the technique you're going to use every single time. The one that we're going to get the highest machine material removal rate on isn't one you're going to go and say, this is what I'm going to use all the time. And Tom and I talked about it, Ron talked about it. But you got to understand that there's three different types of toolpaths here. First of all, you have the traditional style toolpath. And the traditional style toolpath really is about taking your geometry and offsetting it from the outside in or going from the inside out. And with that, what we usually try to do is, 1 times the diameter of depth of cut. Generally, it's a 35% radial. And, there's just certain pitfalls that you can run into that. One of them being is it's going to be hard to maintain that chip thickness based on the geometry you have. So what ends up happening is you kind of, all of us being a machinist, how many times we heard it, in the corner, you hear that sound as it hits the corner. And right away, it's like, okay, what does the operator do to overcome that? The worst thing you could possibly do. He hits the override and adjusts for that based on the worst case scenario. Mm-hmm. So like, Tom and I talked about, what does that do to your tool life? It's gone. So now we look at what MasterCam developed probably about 8 years ago. It's called dynamic motion. And basically what we did is we built upon an old theory of radial chip thinning. Radial chip thinning is basically a theory that happens when you go 50% less on your step over. What you have to do in order to maintain that chip thickness, Tom and I talked about this too, is that's the most important thing to get the heat away from the part. You increase your feed rate. Well, the byproduct of that is your material removal rate jumps, okay? And since we're taking lighter cuts, now I can go to a more aggressive step down, 1, 2, 3, 4. I mean, I think you've got some cutters that can handle all the way up to 4, right?
Up to 6 times D for a solid carbide, and of course Indexable can take you even further.
Right, right. So there's good things there, and you're always doing a climb cut. Well, here's the other problem. People see we're always climb cutting, so I ease in and out of that cut, and then there's that air cut moment. Okay. So how do we overcome that and get even higher? Well, after talking to the guys and talking with Tom, it was one of those moments of, wait, hold my beer, I've got an idea. And we came up with power cutting. And power cutting really is taking the more traditional speeds and feeds that you see, but instead of doing a light, fast cut, we're going to take the traditional speeds and go to a heavy cut where you're going to see 70 to 90% step over. Okay. And then again, it's like, wait, I got one more thing to throw at you. Instead of just climb cutting, we're going to do both. We're going to go bidirectional, climb, and conventional. And with that technique, the material removal rates were just incredible. And I'll be the first to say it, I couldn't believe it.
I must admit, I look at this table here, and there must be about 100 years experience. 75 of them was mine.
You do have more gray.
But there's no way I would even think about those kind of parameters when cutting a titanium. Not what 2D and 80% step over, and doing conventional milling at the same time. So I'm sure there's a lot of people out there kind of skeptical about that. But this little seminar and demo, we're going to prove that it can be done, and at the same time, you're gonna save the tool as well. You're not going to blow up the tool like many of us done.
And let me throw just these three specs at you. So if we look at the traditional cutting method that we did, we had a material removal rate of 0.45. And then if we take a look at the dynamic, we actually cut the cycle time down to 32 minutes from the 58. And we had a reduction of 45% from the traditional. And that material removal rate went to a 1.15. And then if you take a look at the power cut, we cut the cycle time down to 16 minutes with a 73% reduction compared to traditional. And that material removal rate was 2.61.
Of course, you supplied the tool, of course, from Iscar.
Like we do a lot.
Yeah.
He's my favorite guy for MasterCam and Okuma.
There you go.
Yeah.
But just explain the technology of the tool and your input.
Well, the tool that you'll see in the videos that are going to be running, it's a purpose-built end mill. It's designed to machine titanium. So we're optimizing the tool from that perspective. Can you machine other materials with it? Yes, you can. But it was designed for that purpose. And that's just, as far as design, lingo goes, that's edge prep, maybe a T-land on the flutes. So it's designed to withstand the cutting forces that go with machining a high-temp material like titanium. But for me, it's about putting the pieces of the manufacturing technology puzzle together, about looking at the machine, what the machine's spindle capabilities are, what is that machine going to allow us to do as far as the machining approach. And then you got to put the programming together with that tool. So you take a tie turbo, what we call that end mill, the tie turbo, along with the right programming technique and a machine like that we're working with that allows you that flexibility to go, speed or power. And then you got something like what we're going to see here, in the machining videos today.
And what characteristics are the machine that allow this?
The spindle's 15,000 RPM, 30 horsepower, and then we have a big plus connection. So when we get into the heavier 80% step overs, the tool is a lot more secure, and we don't have to worry about it rattling in the taper. When we're doing the 80%, the stiffness of the machine, the spindle, the way it's hanging off of the cross rail, has a lot to do with the ability to keep cut. We have other machines that have different spindles, but this 15K that we're using is very versatile for high speed or like the low and slow 1400 RPM that we're running. So we can get away with both techniques, and we have different tolerance controls that we can use to do the dynamic type finishing that would probably be entailed in this also.
And the cool thing too is when we were running that 80%, you didn't hear anything. You could barely hear it, and it was actually cutting. It was quiet, and we never went over 20% load on the machine. Yeah,
so the machine like that must have to be able to handle a side load, especially 80% step over.
Yep.
Yeah, so that's incredible. I mean, I know for a lot of you people out there, this sounds like it's pie in the sky, but I've actually seen this, and then as we watched the video, we do it dry and we do it wet. Now, we don't recommend you do it dry, but we do it, and it's incredible.
Thanks.
Before you can actually see the actual performance of the tool, and it's incredible.
Thanks for pointing that out. We don't recommend machining titanium without coolant, but to talk about the reason why we came to this and we tried this is the dynamic milling is perfect for controlling the tool, but one of the caveats is the air cutting time. So you get bigger parts where you're trying to maintain the climb milling technique, and what happens? You get to the end of the cut, you go all the way back through air cutting, if you will, and then you got to get back into the cut. So this is where we use the power of the zigzag within MasterCam, but we have to say, hey, can we climb conventional? But if you think about this, if you're taking 70 to 90%, you're almost simulating a full slot type scenario. So you think about the impact load on the cutting edge as it's entering and exiting material. You have a thin chip on entry, you have a thin chip on exit. It's something that you're not going to be able to do this with maybe your everyday average run-of-the-mill tool, but you get a quality end mill, you apply the right programming techniques, and the cycle time reductions, not only from being aggressive in terms of cutting parameters, but just technique of the approach and tailoring that approach to what the machine and what the part geometry will allow you to do. It's a good starting point to productivity, and it's not something for every application. As you mentioned, this is a rigid scenario. It's 2 times D end mill. We're taking a 3/8 diameter and we're taking a 3/4 inch depth of cut. But as the tool gauge lengths get longer, then you go to the other approach, and this is where the machine spindle helps us with the RPM availability. That would allow us to take. Maybe go from a 4-flute tool to a 7-flute tool and use speed as our ally for metal removal as the gauge lengths get longer, and take the light radial cuts.
Right.
Yeah, and one thing we did, the tool holder was a side lock.
Yeah.
So again, people think, but from a security standpoint, I mean, it's not coming out of the holder,
Yeah,
and it's not coming out of the spindle.
Yeah.
So,
and as a programmer or an operator, you're not going to be walking into your boss or your owner's office and telling them that you just scrapped a really expensive part because you pulled the tool out.
I think we've been conditioned over the past couple of decades over what the norms are, what's the flavor of the month. It used to be side locks, or they've all gone. Now we're bringing side locks back. Now for something like this, it's critical it is a side lock. So
Yeah.
it's. We've seen and of course, conventional milling. You never conventional mill. Of course, we exploded that myth. So we just keep reinventing what we should be doing, and we keep exploding those myths and those norms. So this is good.
Yeah, and I think you really got to kind of, in today's day and age, think outside the box.
Yeah.
And sitting down with all of us, I think that was the one thing I really kind of got out of it, because we all kind of brought a different scenario in this. And there's a lot of people out there don't realize that what they can leverage with what they have in their toolbox today. And it was interesting even talking to my boy Blue over here about, the machine tool. We talked about, hey, I want to go light and fast, 560. Okay, well, now I want to take a heavy cut. Okay, now we can still go 560.
Yeah.
And that was one thing I was kind of like, okay, I'm in. This is going to be cool.
Yeah.
yeah, I mean, we've done the linear guide system that's on this machine for over 30 years. So it's not something new to Okuma, and our guides that enable us to take heavier cuts or heavier forces on the machine. It's not new. It's a proven technology that we've used forever.
Well, I think we've probably come to the end of our time now, but this has been a great discussion. We could go on for another hour on this.
Absolutely.
Quite easily, but I'd like to thank Ron Ranaszewski, or Boy Blue, from Okuma, Christopher Cazell from MasterCam, and Tom Ron from Iscar. Also, you'll see our contact information if you want to reach out to us, or email, and maybe some cell phone numbers if you guys want to do that. But this collaboration here wasn't ad hoc. This is all a culmination of our 20-year or nearly 15-year partners and thing to get collaborations like this, and to actually find solutions for our customers. And I think this is one that people are going to like a lot. So again, thanks a lot, guys.
Thank you.
Thank you.